Another thing is if you sum up A over one of the dimensions, it should be 0 everywhere, and that's just because if you look at the formula, if you sum up over all the i's, if you sum up aij over all the i's, over each matrix, or over each element ak, the sum of the 3 gradients should be what? So if you have if we have 3 basis functions that lies on a triangle, every basis function is 1 at one of the vertices and 0 at the other 2 vertices. If you sum up these 3 basis functions, what do you get? The sum of the 3 basis functions should be equal to what at every vertex? Should be 1, right? So the whole basis function should be 1. The whole summation should be 1 across the whole element. Therefore, the gradient, the summation of the 3 gradients should be what? 0, right? Because the summation of the gradients is equal to the gradient of the summation, which is a constant, right? So if you sum over the gradients, should be 1. So therefore, when you sum over each row, you should get exactly 0 for the matrix A. Okay, and that also, of course, means the matrix is singular. We haven't defined boundary conditions yet. The matrix without the boundary condition is going to be singular. All right. So now let's figure out how do we set the boundary condition. So now we have here, remember we figured out all the boundary indices, IB. So let's define a logical array that is equal to, is true for all the interior points and false for all the boundary points. So let's say, okay, interior is equal to 1's number of points, 1. Okay, interior is equal to, okay, so let's say we already have IB, right, being the boundary points. IB, is it IB here? IB, yes, is equal to 0. So interior is going to be 1 in the interior and 0 on the boundary. And let's convert it into a logical array, so that instead of 1 and 0, it'll be true and false. That will allow us to index the matrix with that logical array. So my A is going to be A interior. Okay. So that'll reduce the dimension of the matrix, get rid of the boundary dimension, the boundary grid points that I don't need in the matrix. So if I run that, IP, okay, MP, yeah, thanks. Okay, it ran, and so my A, I think, is gonna be, yeah, its dimension is reduced. It's no longer 406. It's reduced by 70, which is exactly the number of boundary grid points. And now if you plot the summation of A, it won't be 0 anymore. It'll be occasionally non-zero for, so if you have any basis function that neighbors a boundary grid point, the summation won't be 0 anymore. Okay, so let's also plot the eigenvalues of A just to make sure we get so the eigenvalues of A, they are positive, so you shouldn't get anything that is 0. Okay, that's good. So we get a positive definite matrix. Question so far? Seems like it's working so far. Now we have the matrix A. The next step is to figure out the right hand side. So Bj is equal to an integral over the whole domain of phi j times f. And we set our f is equal to 1 in this case, so it becomes integral of phi j dx. Again, we split that up into the elements. It's going to be an integration of phi j at the element k dx. This integral is only non-zero in a small number of elements, right? 5 or 6. And on each element, phi j is a piecewise linear function. So on each element, let's say each element is we have the triangle. The function is like that. So this is phi j, and we have x and y. So phi j is going to be a linear function. If I draw the contours, it'll be like that. The integral of phi j over this triangle here is going to be the volume of this tetrahedral, right? The height of this tetrahedral is equal to 1. The base is calculated as the area of the triangle. So this is equal to what? The integral, which is the volume of the tetrahedral, is equal to what? Yes?
1/3 times the base, sorry.
Yes, 1/3 times the base, which is ak, times the height, which is 1. Right, so it's ak over 3. Let's code it up here, ak over 3. The right-hand side is going to be also 0 of mp1, right? And after I compute the matrix, I compute the right-hand side. So bi1, the first, is equal to ai divided by 3, right? And all the other corresponding right-hand sides are going to be done in the same way. They all the integral are all the same for every basis function in that triangle. Of course, different basis functions are associated with different set of triangles, so the b is going to be different, but like the contribution from the same k for all the 3 basis functions on that triangle is going to be the same. So now we have a b, but the dimension of b is still too large. We need to remove also all the boundary points. So b is going to be b interior. Right? Let's run this. Oops. Okay, so that seems to work. We get a 336 by 336. We get a b 336 by 1. So let's also define a u. U would have to be covering, in order to visualize u has to be 0, mp, and 1. But then we're going to set u of interior to be the solution. It's going to be a \b. All right. So that gives me the solution, the height of the interior basis functions. The boundaries are going to be left to be 0. So after this, let's run to see if that works. Oops, zeros. Okay, that worked. We get a u. We get a u that is it's a bunch of zeros. That's probably boundary. Yeah, we get a bunch of non-zeros. So let's visualize that. Let's use the twice surf again. We use the t should be the same, this should be the same, and we just use u, right? Okay, that's our solution. So this is our boundary, and we are just solving the Poisson's equation with the constant right-hand side, which means the curvature or the Laplacian of the solution should be -1, right? So it bumps up the curvature in the x direction plus the curvature in the y direction should be equal to -1. And that's the solution we get for the two-dimensional Poisson's equation. And the boundaries are 0. Okay, so that completes our demo of what how do we solve how do we use finite elements for a two-dimensional problem. Any questions about the procedure? Yes.
Back when we showed that shape, like that's the original spike of the basis functions, and then you see something like 5 or 6 like edges. Like, why was it not a triangle?
Oh, yeah, so each triangle is shared by 3 basis functions, but each basis function doesn't neighbor only 3 triangles. So let me try to draw it. So we have a triangle here, we have a triangle here, and we have a triangle here. For example, we have a triangle here. This basis function, if I draw the contours of that basis function, the basis function looks like that. The value of the basis function is 1 over here, it's 0 over all the other grid points. So the contour looks like that. I said it's 5 or 6 because the basis function is non-zero. In this case, in 5 elements, 5 triangles. Is that the question you were asking?
Yeah.
Okay. And you can imagine, I can easily have another basis that is non-zero in 6 elements, right?